Greetings. Let's begin by looking at the theorems we want to consider today, one each by Wieland, Flavell, and Guralnick-Tracey. We want to see how they may detect whether or not a given test subgroup is contained in a proper normal subgroup. If you look at the first one by Wieland, this is kind of a classic. He's a pioneer of subnormal subgroups. And essentially what his says, I mean, every one of these theorems the first requirement is that the test subgroup we're interested in is contained in at least two maximal subgroups. The Wieland theorem requires, in addition, that the test subgroup H is subnormal in every maximal subgroup of G containing it. In comparison, Flavell will allow you to have one of the maximal subgroups containing the test subgroup not be subnormal. And further, Guralnick-Tracey has a completely different criteria that isn't really clear how it's related to the others. That Guralnick-Tracey criteria is the set of descending normal closures, we'll talk about that in a minute, of H with respect to each one of its containing maximal subgroups has a unique maximal element. Okay, now I just want to mention that the reason I'm doing this is that I did do this and I used a kind of a Maple computational analysis because it wasn't really clear to me how Flavell was related to Guralnick-Tracey. Wieland is a classic theorem, and you can find a nice proof of a logically equivalent version of it in Martin Isaac's book. Flavell's theorem, well, there's the published paper there. Flavell's theorem is one of those theorems in pure group theory that it's really kind of opaque. It's so complex, and it begins with, basically it's an indirect argument. It's a proof by contradiction. It begins with suppose not, and then after that there are about 5 small claims, not clear how they're related, with some more basically proofs by contradiction in the middle of all those, and finally you get to the final contradiction. So my point is that in Flavell you don't really get a lot of insight if you just change the hypothesis a little bit. What happens? You don't see it. Okay, and furthermore, it's not clear how Guralnick-Tracey is related to that. Now, what I've done today is I've found a way, just computationally trying to evaluate these two and compare them, how to change the hypothesis of Guralnick-Tracey to one that really is much more compatible with the other two theorems. In addition, Guralnick-Tracey, basically in their paper, they showed that their theorem implies, right, the Flavell theorem. However, in the proof of Guralnick-Tracey, they use Flavell's theorem. So it's possible, one might wonder whether or not Flavell also implies Guralnick-Tracey. Well, the examples I showed today basically show that Guralnick-Tracey is strictly stronger. Okay, so that's a couple of interesting things we did. Now let's just look at a couple of definitions real quickly, and then we'll get into it. So H is a normal subgroup of G, just in case, if you look at its conjugates, it's stable under the conjugates. What's a conjugate? You take G and you multiply on the left, you multiply your subgroup H on the left by G and on the right by G inverse. And if you get the same thing back again for every G, then that's a normal subgroup. On the other hand, a subnormal subgroup is just basically a sequence of these normal subgroups. So you start at H, and then you're normal in the next one, normal in the next one, and you're able to find a sequence all the way to G, and that's called a subnormal chain. Now, one more definition, actually a couple more, but if your subgroup is not normal, then you may extend it to a subgroup that contains it that is normal, and indeed a smallest one. It's called the normal closure. And so what you do is you take all the GHG inverses that are not equal to H, and you use that to generate another subgroup. Okay, and that's called the normal closure. Now, the one we want here is the ascending normal closure. We want to iterate that. So we're going to do a normal closure, get an answer, do another one, get an answer, and keep going. Now, these are finite groups, so eventually we have to have a fixed point. And that fixed point is the descending normal closure. Okay, so just quickly, let me show you an example of a group. By the way, this is a Shepard-Todd group, or number 22, and these are all in Don Taylor's book, and I implemented all of them, and it worked perfectly, right? So that's a wonderful set of generators there that you get from Don Taylor's book. Further, Don Taylor also gave me generators from some other groups that were not Shepard-Todd groups that I use in this paper. So I'm very grateful to Don Taylor for his help. Okay, so notice that everything that's blue, all the blue subgroups are normal. And notice there's no annotated little numbers here. The annotated little numbers basically indicate how many conjugates you have that are different from the original. So you have this equivalence class of conjugates. And so when you look at maximal subgroups, and this was pointed out to me early by Gareth Tracy, you have to consider all the conjugates. So if I have a test subgroup, I have to see how many of these, or maybe more than one, right, that it's contained in when I actually, compute the descending normal closure. So that's an important thing. All right, so that gets us started here. So let me go ahead and go down and just quickly look at some of the code. And you can see this document is pretty big. Okay, so here I'm generating a different subgroup. This is a Shepard-Todd number 13. It's of order 96. And just to give you an idea of what these matrices look like, that's it. And then we get the C4.6 S4, the group we claim to have gotten. Okay, now let me close that. And what we need to do is, so we need to create the ambient overgroup or supergroup, and we also need to create all the subgroups and all the conjugates of the maximal subgroups and the test subgroups we're interested in, right? So basically, I've done all that already here, and now what we need to do is we need to determine which one of the maximal subgroups contain our test subgroup. So the test subgroup that we're looking at here is a copy of C2, okay? And so when we do that, we end up getting that, okay, so the test subgroup is contained in one of the M4 type maximal groups, and it's contained in 3 of the M5 type maximal groups. Now, just for this example, this is M1, M2, M3, M4, and M5, so it's not contained in any of these. So once we've done that, then we can go actually compute the descending normal closures. Now, I actually compute the sequence so I could see who the intermediate groups, what they were. And so here's our first, this is our test subgroup C2. And then this is the first maximal subgroup I'm looking at to find the descending normal closure. And so what I do is I end up iterating and looking at all the steps of it. And the first one I get is the poly group. Then I get C2 cross C2, and then I get C2. Okay, so I get it back again. I think I want to make sure it's exactly the same group. And then I do it with respect to, this is 3 conjugate copies of, this is C4 circle D8. And I get D4, C2 cross C2, and C2. And then I get 2 more conjugate copies, and I get something similar. Then I just kind of accumulate all these down here so I can see what they are. And I see, okay, now I have, for each one of those descending normal closures was a group that was isomorphism type C2. I want to make sure that, in computing, you want to make sure everything is what it's supposed to be. So I'm going to check that these are all equal. And in addition, it's equal to my test subgroup. And I do that. And that's good. Okay, now one thing I haven't done is so now I've got the Guralnick-Tracey criteria, but I don't have the Flavell. The Flavell criteria requires that the test subgroup is subnormal in all except possibly one of the maximal subgroups that contain it. Okay, so I have to find a way to compute whether or not the test subgroup is subnormal in those maximal subgroups, right? So I have another method that I created, and I didn't really know I was going to use it, but it's basic. It will give you the subnormal closure. So that's the smallest subgroup containing the test subgroup that's subnormal in the ambient group you're interested in, right? So basically, I did that, and furthermore, so here's my test subgroup C2. This is my first maximal group that it's contained in, and then I'm going to compute closures. I computed the subnormal, the normal closure, and the normalizer. While I was at it, I just computed them all because it's interesting to look at them. And for the subnormal closure, I got C2. And then I did the second one, and I got C2 for that. So in fact, I got C2 for all of them. So basically, if you summarize this in a table, you can see that for these maximal subgroups over here, we don't have any containment in the first 3, but we have 1 copy that contains our test subgroup here, and 3 copies that contain our test subgroup here. It turns out that, by the way, in this, red means our original test subgroup, blue means normal. So the CSU2F3 is normal in the ambient group G, and GL2F3 is, and C4_A4 is also, right? So those are the normal subgroups. This is my original test subgroup. So what happened was I see that I get exactly the same thing for the subnormal closure as I get for the descending normal closure. Okay, so that's going to be a key thing. Let's go over and look at a couple more examples. And so here's exactly the same subgroup we were looking at. So that's exactly the same table. And then I just show a couple more examples of that. And by the way, I should point out that, yeah, if you take the set of descending normal closures for Guralnick-Tracey, yeah, you get it has a unique maximal element. It's the original test subgroup itself, right? So not terribly interesting. But there's another example with a different kind of setup. You have lots of groups here. They're all equal to your test subgroup. And then another one. So here we have something different for this test subgroup. We have effectively, D4M1 is subnormal in this containing maximal subgroup, and also it's the descending normal closure. Similarly, GL2F3 is the subnormal closure of our test subgroup, and it's equal to the descending normal closure. So these are equal where I'm seeing now. So that's my I would say my clarification to make the connection of these theorems not so opaque is I can use the subnormal closure for the hypothesis in the Guralnick-Tracey theorem, and that really then kind of the light bulb went on. And by computationally doing this, I didn't even know I was going to use it until I tried to do it. So that's where computational exploration, in my opinion, really gets you something, some kind of insight you didn't have before. And maybe somebody see that already. I mean, now it seems kind of obvious to me, but it didn't initially. Okay, so if you go to this example, then effectively what we have here is a situation, the first situation in which Flavell doesn't hold, right? And that's because all these subgroups here, there's only one of them that's subnormal in the containing maximal subgroup. These other three aren't. So Flavell fails here, but Guralnick-Tracey works. And then you can get all kinds of cool looking pictures here. For this example, we end up having two conjugates. The little g is just an arbitrary conjugate of S3. And so we get all these guys, and there's our set of descending normal closures. And our maximal element is GL2F3, and that's also the containing, normal subgroup of our ambient supergroup. Okay, and so you notice that in each one of those. Remember, blue means normal. Okay, so there's several more. Let me you can get all kinds of pretty pictures here. A couple more things I want to point out real quick, and that if I get there, I did a lot of these. That there's correct non-detection. So in this case, our test subgroup, right, is not subnormal and not even contained in this maximal subgroup. So we don't have a maximal element up here in its set of descending normal closures. Similarly, there's another one like that, and then I'm going to go down to the bottom now. I want to show. Okay, so then also it's possible not only for non-detection, but also it doesn't have to be subnormal. The test subgroup doesn't have to be subnormal in any of the containing subgroups for Guralnick-Tracey to work. Okay, so notice it's not in this picture at all because basically it's when we compute the subnormal closure, we don't get it, or we compute the descending normal closure, we don't get it. Okay, so similarly, there's a few examples of that, and then I'll just go back up here to the top and maybe summarize a little bit if I have another minute or so. Okay, so what we're able to do then is we're able to replace the descending normal closure that we look for a maximum element with the subnormal closures. Okay, and that really just then links up and makes all the connections less opaque, in my opinion, right? Because now everything's in terms of subnormal. So what we did was we basically have that nice kind of modification that makes everything clearer. We also showed Guralnick-Tracey is strictly stronger than Flavell, and also this led to us showing that one of the other theorems in Guralnick-Tracey's paper was actually equivalent to their theorem here. Okay, so I think hopefully I'm within the time limit there, and so that I can end there.
Very, very good. Just as a point of order, anybody in the audience can unmute and ask a question, or you can post it to the chat. So John will take questions now. So John, am I correct in thinking that this is primarily a research project? Have you found a way to bring it into the classroom as well?
Yeah, I mean, group theory in high school is not a normal course, but I have like students in math club and also independent study students that I've taught this stuff. Not this particular example, but a lot of group theory. So yeah, so I'm thinking about them when I'm doing it.
This would be very motivating for high school students to see. Um,
Yeah, thank you for saying that. The It turns out that what I try to do is I try to kind of marry computation with mathematics. So there's a lot of kids that are learning, they're both in, AP computer science and advanced computer science classes. And so, it is kind of more stimulating and also provides another method of understanding as opposed to just abstract group theory. As I said, some of this, the proof of Flavell's theorem is really opaque, right? I mean, hopefully I will figure out why that's, a good way to understand that, and hopefully the kids will too.
Very good. Thank you.
Thank you.
If you could stop sharing, we'll move to the next presentation.
All right, so I'd like to introduce our next speaker, Phil Yasskin. So Phil, if you'd like to share your screen, you can go ahead and get started.
Hello, everyone. I have written a calculus book, and it is totally online. It's self-published, and I'm trying to get it adopted. And so I will take this web address and put it in the chat. Chat, where is chat hiding? There it is. And it has to go to everyone, not just Robert. Okay. And at that website, you can see approximately half the chapters. So here's Calc 2. There are available chapters in Calc 2 in the sample on area, average value, mass, center of mass, volumes, polar coordinates. And they're complete chapters, so you can actually evaluate what is there. Back to the main page, I have a page called Benefits, which will help you see various things that are useful in the book. And a lot of them are graphics. So, for example, here is an animation showing linear approximation. The function and the tangent line merge before they actually reach the point. They're merged now. And so it gives the students an understanding of the interval on which the linear approximation will be good. Inverse functions. Here's a graph of a point on the function f and its inverse function g, helping them understand why it's a mirror image. And then here we see the inverse, that the slope of the tangent line is a reciprocal because the rise-run triangle is again a mirror image. And that gives a reciprocal, but the important thing is that they're at different points. And so that's a graphical derivation of the inverse function theorem. There are places in the book, such as graphing functions, where they've found everything under the sun about a particular function, and now they need to assemble it. So they add points. They identify the critical points with little horizontal lines. They identify concavity to give a minimum at that point and an inflection point at two other places, and then they can connect the dots. And they can go back and look at various aspects of putting together the graph. Exercises on related rates. There are lots of pretty pictures. This one here was made by a student as a project in my summer program for middle schoolers. It wasn't quite so refined, but I worked with him and we refined it and got it good for a related rates problem. Excuse me. It's the morning and my voice sometimes gets congested. Then he started working for me and he made all the plots on this page. This one should be the policeman watching the car speeding on a perpendicular street. Milk spilling on the floor, etc. Okay, this shows area as a antiderivative of the curve. And so given a function f of x, we have the area function under it. And we would like to prove that the derivative of the area function is the original function. So proofs are frequently hidden buttons, so they're available for the better students to read. So here again is the full area function. And there's the formula for the limit definition of the integral. So we want to look at the numerator. It is the area of a of x plus h, which is in purple and green. A of x is just the purple part. So a of x plus h minus x is the green part. And as h goes to 0, that area gets smaller. And if we divide it by h, we get the derivative. So here we approximate that area by a rectangle, and the area of the rectangle is the base h times the height f of x, h times f of x. When you divide that by h, you get back to f, and that's basically the proof of the fundamental theorem of calculus, basically done graphically. Volumes of revolution. Let's see. Solids of revolution. Sometimes the graphics take a little time to come up, especially on a page with lots of pictures like these. And then when you do a Riemann sum slice, you can see that the slice can become a disc, a washer, or a cylinder. And I emphasize to students not to memorize which is which, but to think about which comes from which. And then here in the exercise pages, every exercise gives them the problem, gives them a chance to work it. They might look at a hint. And after they have an answer, they can check it against the answer. And if they're really having trouble and they try again, can't get the answer, they can read a full solution, which has several graphics in the solution, helping them understand how the slicing is made, how it revolves, in this case, to make a disc, and how we accumulate discs to do the integral. I can show you how some of these are made. So I have a Maple worksheet here that is specifically for this exercise page. So there is the code that makes this animation, which shows a slice revolving into a cylinder. And then here, the cylinders are accumulated to fill out the volume. And that's basically how the integral is done also. Okay, plotting polar curves. Here is the cardioid, graph it rectangular, then start filling in quadrants. And here's an animation of how you sketch the curve. Here is the animation of Taylor series approaching the sine curve. And after you get to like the 11th Taylor approximation, you have an excellent approximation of the sine. And I can tell students that's how a calculator can calculate the sine. Here's the two-dimensional version of linear approximation, where the function and the tangent function merge before they actually reach the point. Propositions in Calc 3 for the gradient. We want to know that the direction of the gradient maximizes the directional derivative, and there's a graphical proof. Also, here is the fact that the gradient is normal to the approximations. And so this is the proof. Stokes' theorem, what is hard is understanding the relationship between the normal and how you go around the boundary. And this actually has a hand which can show you going around the boundary. The hand is not made with maple. It's superimposed on the maple graph. Okay. And on the next page, you have the hole, how you go around the hole, and the hand when you're on the inside and outside. Okay. Okay. I'm ready for questions. Thank you.
Thank you, Phil. That was great. So now if you have a question, please unmute yourself and ask, or you could type it in the chat. It looks like we have one question here. Have you created Maplets based on these applications?
No, I've stopped making new Maplets. However, somewhere in the chapters, let's go to Calc 1, Applications, Area. Wait, I'm sorry, Integration, Applications, Calc 2, Applications, Area, Average Value, Tutorial. We have converted some of what used to be the Maplets into things where students can guess the average value and then calculate the average value and check their steps.
Awesome. A second question here. What software are you using to create the web page?
HTML and LaTeX and some JavaScript.
All right.
Well, there's a lot of JavaScript in the background. I don't do much of it. Much of it was made by my honors students.
All right. Are there any other questions for Phil?
I should say this graphic is not Maple. Unfortunately, I wish Maple had a way for me to export interactive graphics like this and actually put them in the web page. I would easily convert because these are much harder to make than the ones we had in the Maplets.
Anyone else?
Just a quick question.
Yep,
Go
go
ahead.
ahead.
I just wanted to ask if it's only it's just the static stuff, or there is an actual programming language behind this, like Python, bringing out the calculations.
These calculations are being done with JavaScript. Mhm.
All right, so thank you, Phil. You could stop sharing your screen and we will move on to our next presenter. So at this time, I will pass the floor to Scott Gould. So Scott, if you'd like to share your screen, you can begin.
Okay, good morning, or actually, well, it is here. Hi, so I'm Scott Gould. So in my talk today, my goal is to make you a celebrity. I want to ensure that you have a seat every night at the French Laundry, Le Idiot, or a Hungry Heifer, and have millions of followers on your social media site. So how am I going to do this? Well, I'm going to get you into pictures. Why would people want to see your work? Because you use Maple. There's a large pool of viewers out there, and they are hungry for education. They are looking for stuff. 2.5 billion unique viewers on YouTube. Maple is a large, or significant fraction of that YouTube group. Teaching these days has moved from essentially the stand-up classroom where we all sound like Charlie Brown's teacher, rah, 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 to other techniques such as the ones that Phil has shown today. Okay, key is emphasizing conceptual learning, content, and particular procedures are moving away from reading to viewing.
Sorry to interrupt, Scott. I think you might want to share your screen. I don't think we can see your screen.
I shared my screen.
Okay.
Shared my screen. Share. Oh, so you're telling me I've never shared my screen?
Yes.
My
Yeah.
apologies. Okay. All right. Well, anyway, so here we are. So large viewers, we've heard learning techniques, emphasizing conceptual learning, the content. The key is, of course, we want the students to be able to control the pace at which they learn. Some learn faster than others. Our goal is to provide tools they learn by doing. So I got to get off my, this is the soapbox that Robert Lopez jumped onto with me yesterday. Okay, moving on. Maple specific content available in terms of videos, unfortunately, is really poor. There's Robert Lopez, and then there's this tremendous dive down to what other people are doing. I've seen a few good stuff, but a lot of people are saying, "Oh, I did a little bit on Maple. I have no idea what Maple really is, and so here is how I can get more clicks onto my YouTube account." In addition, this is a little criticism of those who do hold the Robert Lopez videos. Maplesoft has made a lot of actually very good videos, but they are poorly organized. It's difficult to send your student to the Maplesoft website and say, hey, here's how you're going to go through all the videos for, say, calculus or vectors or something like that. So what do you need in order to create videos? Well, certainly you need the video distribution website with a large pool of potential viewers. I use YouTube because I have a Google account. Okay, you need editing software. You don't have to buy expensive stuff. I actually do use Camtasia. It was recommended to me by Robert Lopez. I paid $180 US, and I've never had to upgrade since 2020. All you need is a few things. You got to be able to record the screen, cut the mistakes, and definitely do intakes. I cuss a lot, and so apparently that's not allowed or expected on YouTube. Okay, understanding dimensions. We'll talk more about that later. And unfortunately, you have to have a lot of time. It is astonishing how long it takes to make 1 minute of video if you want to do it well. If you just want to stand there and have them record you babbling, then it doesn't take as much time. Okay, so let's say you have decided to create your YouTube channel. So here is my YouTube channel home tab. Okay, and I can put up here an introductory video so that if someone goes to the channel, they see the video, which describes what goes on in the entire channel. This is a playlist. Think of it as your textbook. So here is my textbook, which was motivated by a discussion that I had with Doug Mead in the very first Maplesoft conference back in 2019. Here's another textbook. This is the one I'm working on now, learning physics using Maple. Here's one involving shorts. We'll talk about that. And of course, you can also add on information about other useful channels for people to go to. So what's the key? You've created your channel. The key is you want to create playlists. Again, playlists are the textbooks. The videos are the chapters. The advantage is you can sequentially put your chapters in the order that you would like people to watch them. Key here is to design a thumbnail. This turned out to be something I didn't realize was so important. By the way, I made a lot of mistakes, and so I'm hoping to prevent that from for anyone who wants to take it up with me. Thumbnails, that's what everyone sees. So if you see the same thumbnail or they see it in big screen, they are more likely to click on it or not click on it, depending upon their interest. Okay, tag each playlist and video with the appropriate terms to help the search engine. I found out I got a huge number of hits by just putting the word in tutorials. So you're ready to actually make your videos. Well, there's two types of videos. There is the generic video, which could fill into by 1960 by 1080, or 1920 by 1080, but we'll talk about it. You'll notice I've actually made mine a little less wide. Here is your short. This is like your TikTok video. This is the thing that you see on the phone. I recommend, unless you are incredibly articulate, write a script. Okay, I also suggest a 15-second introduction. I used a ramble for 30 seconds, cut it at 15. That's about the attention span they have for videos. So the question is, do they want to continue to watch this video or not? Put a human interface in your presentation. Show a human. As much as I love Robert Lopez's work, I wish I could at least see a picture of him. But he says, no, that's not going to happen. Don't waste valuable video space. We'll talk a little more about that. Obviously, redo mistakes and edit out wasted audio. It's amazing how quickly students lose interest if they feel that you're going and we have experience with that because we have set up another video channel and it was not as well done. It is not getting as many hits, even though its content is probably more popular than the one I do, or should be. Create shorts to increase your viewership. So again, it's amazing. These 30-second shorts really do a difference. And of course, something that has been really good actually on this conference is make your visual content large. But the problem is, here is and I apologize to the person whoever made this. Here is an example of what I saw filling up half my page on my screen. Here is my work filling up half my screen. It's obvious which one you can see much more easily. And in fact, the goal here is by filling the screen with half my video, you can take the other half to put up, and this is on a laptop, your own work so that you can work on your own stuff and click and go and reproduce what was on the video. Okay. End of screen recommendations. When you get to the end of video, one of the nice things is you can put in links at the end of your chapter. So here's one on the third one of the fundamentals of Maple, which you can either go back to chapter 2 or move on to chapter 4. They just click on it. All right. So let's talk about metrics. Let's talk about so first thing is, in order to get people to look at your videos, there are the impressions. This is the number of times that all-important thumbnail of your video shows up to the viewers. Then, if they actually click on your thumbnail, they get a view. And guess what? If you get 5% of your thumbnails being clicked on, you're doing really well. Likes, obviously, if they like your video, then they're going to get more impressions to see more views. Eventually, of course, they watch it. 50% of the people who watch your video drop out within the first 30 seconds. So if you've got a 12-minute video, don't expect everyone to be there at the end. Then, of course, if they really like it, they subscribe to your channel so they'll get information about the subsequent and newer releases of videos. The yellow ones are the ones which you could need in order to monetize your work. So let's take a look at what the analytics you get from this. So here are the impressions. This is just my videos as opposed to the shorts, okay, or the YouTube stuff. All right. And here is the information, and you can see with time, and this is when I dropped a video, and we have no control. Then you can look at how many hours they are watching. This is over the last 90 days and how many views and how the subscribers increased. And if you want, you can even see what people are viewing at that time. My goal is to make sure that I don't have any more zero viewing hours. But anyway, but again, notice again, getting started, that introductory video, which when I put up, that also made a big difference in getting things started. All right. Let's see. Last other channel, you can obviously get, unfortunately, in my class, more than half the students are women, so this is a very odd demographic for me. Most of the students, people are younger. During the summer, I noticed this number goes up quite a bit, and most of the people are coming from the United States, which is not surprising here. By the way, and of course, they can even click on closed caption, and so I was surprised about 8% still use English for closed caption. So there's the deal. That's what I want you to do. Get out there, get your message about Maple out there. Oops, and that didn't work. Well, that was kind of a bummer. Let's go back to, and all right, let's go back. And I lost my, okay. And I think, all right, then I'll just end there.
Thanks, Scott, for that very insightful talk. So now if you have a question, please unmute yourself and ask, or you could type it in the chat.
I have a question, Scott. So say you have
Go ahead.
mixed content. Can a user subscribe to a playlist, or do they have to subscribe to the channel?
As far as I know, they subscribe to the channel, but again, because made effort to put it in the playlist, whenever I do something new, I insert it in the proper place. And then again, I put the links so they can go to previous or subsequent chapters.
I think you're doing actually really well if you can get 1 minute of content out of 30 minutes of effort. Actually, that's really good.
Yep. How do we stop sharing? Stop sharing. Yep.
All right, so I just have a question. Are there certain topics like solving symbolic problems or vector products that are more popular than others, and why do you think that is?
Yeah. So there's no doubt there are two things: solving just an equation. So people are told by the instructor, use Maple to solve this problem algebraically. That gets a big hit. The other one that's very, very popular, even though it's one of my least efficient videos, is linear algebra. That is the number one video watched. And most of it is on how to get enter matrices, working with matrices, stuff like that. So.
Awesome. All right, thank you, Scott.
Ask one more question.
Yep, go ahead.
So Scott, this is Doug. How many of your viewers are your students, and how many are others from other places? And do you have any hotbeds of sources of viewers for your videos?
So I basically brought this on the summer of 2023, and I had did not work on it for about 6 months. I had some viewers in the spring, so spring of 2024 from my class, but that's going to be 12 to 14 people. It really took off basically after that, and it's been increasing exponentially, as you can see. And I got a hotbed during the summer from Malaysia. You don't know where they're coming. But again, here's the advantage is that you have a pool that is universal. And everything that I've gotten is a positive feedback. That what I suffer from is getting the message out there. If you type in how do I learn Maple tutorials, there are going to be a whole bunch of, and if you can find mine near the end, you might find it. The hope is, of course, as more people look, that where I place on how do I use Maple gets pushed up.
Yeah. So, I mean, I could see, or I remembered back that conversation we had before you mentioned it, and said and recognized this as the the new version or the new implementation of the getting started with Maple book that had been written before, and you're gonna, yeah.
That actually was my motivation. And in fact, you and I, we had a discussion about the biggest issue with Maple at the time, and I still think it is the help. And that it's, if you say, okay, I need help on desolve, you get, now they've done better. Okay.
Sorry,
But at the
sorry,
time,
Scott,
it
I
was,
have to jump in. Maybe we can continue this over the lunch
oh, we
session.
have another video. Okay.
Yeah, we've got one more
Apologize.
presenter. So I'm going to introduce Almir Aniyarov, who's going to talk about methods of solving differential equations.
Yes. Hello.
Yes, you're on.
Okay, 1 minute. This is my share screen. Yes, my name is Almir Aniyarov. I teach math in Astana International University in Kazakhstan, from Kazakhstan. This work is joint with Daulet Nurahmetov. We discussed here how to construct green function for second order differential equation with variable coefficient. Yes, and I want to share you how we construct for green function second order differential with constant coefficient. Yes, here's we know in classical textbook of differential equations is some steps we do where is a constant coefficient. And the first step is write equations for delta functions, and second we find green general solution for equations where is for homogeneous differential equation. After then we find characteristic equations where we take a solution when we do two ways where is lambda 1 is equal to lambda 2 or lambda 1 is complex solutions. Yes. And we can do right third step is define that G is a separately for X, and we use continuity condition for green functions and the jump condition for derivatives. For it says green functions conditions, and after then we solve apply boundary condition for differential equation. Our differential equation homogeneous differential equation like this form, first this form, and after then we solve original equation look like these forms. Yes. And the realization of in Maple we do automatically. We give the ABC coordinate, coefficient ABC. Then we do like we give maybe any A, B, C, and F. We take for constant coefficient solution, some solution, and compare with ODE in Maple. Look like we see the solution is same. Yes, it's for constant coefficient for green function. And we do construct for variable coefficient this method. Also for variable coefficient look like this form, differential equations with the second order. And here we do also some steps constructed for green function. Firstly, we split differential equations like this case and impose continuity conditions. Also use jump conditions for derivative. Look like this form. And after then, we solve the homogeneous equations. This form, yes. And after then, we find A1, B1, A2, B2 coefficients and write solve these equations. And after then, apply boundary condition of differential equations. We write the green function. After then, we can do last step is solve original differential equation with the green function look like this form. And I can show two examples maybe. Firstly, I construct green functions. Firstly, we solve look like homogeneous these differential equations. Check ODE at this form. Use boundary condition. And the second step, I construct of differential equations use the boundary condition. Left side and the right side. And I find A1, B1, C1 coefficients, AS, BS. After then, I can third steps, do third steps, solve boundary conditions, jump condition, continued conditions. I find these coefficients. After then, I can do construct green function, look like this form, and I do any right-hand side fx functions, continuity fx functions. I do this as a one, any functions, and then solution look like this form. In the to compare, I solve also my differential equations in the use Maple ODE function. And I can see in the graph the solutions of same. And I can do construct any differential equations and teach my students on the work used in Maple. Write some scripts look like in the Maple sheet. So and this also same. Any f function, maybe you use this x, any continuity functions. Any use this other boundary conditions. Thank you. I finished.
Very good. I guess we can open the floor to questions. Either unmute yourself or post something in the chat. ODEs are great for modeling real life applications. What were you modeling in your classroom as an example using Green's function?
When we use differential equations, topic differential equations.
Were there any applications that you in particular you were looking to solve with this?
When we solve any application, physics equations, any applications, when we find when we cannot solve differential equations with variable coefficient. After then we punctate disk when is not.
I have a question.
Yes.
Green's function, I've used Green's functions myself. And the reason that I do it in Maple and not use the result from dsolve is because the form is easier for certain purposes. So do you explain to your students why you are showing them how to use Green's functions rather than just use dsolve? Because it gets the same answer. Just question why.
In Maple, Green function not constructed.
Oh,
Yes.
it does. You
Yes.
solve for
We
an inhomogeneous problem. It gives you the solution where the integrals are actually sometimes carried out. But if you give it a right-hand side with just a symbol, f of x, it will give you the Green's function as an integral, but it's inconvenient. It doesn't look like the Green's function. You can combine it in there. So this was my experience. I was just wondering if you had done this comparison yourself. It's okay.
Okay.
So what kind of class are you using this in? What kind of students is it, and what's their background?
Third years students in mathematics specialization. 3rd years, differential equations.
Thank you.
Okay, great. I think we have about 15 minutes before the next keynote session. So we can conclude this segment of the conference in the morning, and hope everybody will see you back at the next session.
Thank you.
Thank you.
Bye-bye.